So we've been drawing Lewis structures for covalent compounds, but it's important to remember these are actually 3D structures. So let's look at our VSEPR theory, which stands for the valence shell electron pair repulsion. All right, valence shell electron pair repulsion. Okay, so we're going to draw this and see what we can figure out. Our electron pair geometry may be an A2. In this case, we have one bonding pair, which I'm just going to write as 1 BP, and these are going to be our 7 diatomic elements. They have a shape which is linear, a bond angle of 180 degrees, and their structure is going to look something like this, all right, where A is whatever element. So if we were to look at a diatomic element, I have one right here, all right. I have two of the same element bound together, and here's our bond, and you can see that this is a linear shape. And it does have an angle of 180 degrees. I can take one of these elements and replace it with a different element. Okay, so I replace it with something different. So I just took off an element and it's a new element. So I'm going to have a new letter. All right, since there's no longer two of the same, I'm just going to use X. So in this case, AX has one bonding pair still, and a bonding pair is the bond that's holding the two atoms together. So it has one bonding pair. It is still linear with a 180-degree angle, and is going to look something like this, AX, which I have here on my model, AX. Now, I can take and put AX2. So now I have a central atom, A, and I have two X's, AX2. In this case, I now have two bonding pairs. A bonding pair is the bond itself. So I have two bonding pairs, but I am still linear in shape with a 180-degree angle. All right, what if we have a central atom surrounded by three things? So that is AX3. Those three things could all be, let me zoom out a bit so we can see. Those three things could all be atoms from the periodic table. All right, so different elements. If I have three elements, then I have how many bonding pairs? 1, 2, 3. I have 3 bonds. So in this case, our shape is trigonal planar. The angle is 120 degrees, and it's going to have our shape that looks something like this. Okay, so here's my shape. I have 3 bonding pairs, and this is a 120-degree angle. Now, what if I remove a bonding pair? I now have a lone pair of electrons. I have 2 bonding pairs and 1 lone pair. I still have 3 things around the central atom. 1, 2, 3. I just have made one of the bonding pairs a lone pair. So 2 bonding pairs, 1 lone pair. In this case, we say the structure is bent with an angle that is less than 120. And we have removed this X and replaced it with a lone pair. So why is this important? What happens here, this lone pair is electrons. Electrons are negatively charged. Like charges repel. So remember, we have electrons flowing around these central atoms in their lone pair form. All right, so they may have central atoms flowing around. For example, if we went back to a worksheet that we did, right, this chlorine had lone pairs around it, for example. So remember, there are electrons here, potentially. So the lone pair of electrons, these electrons up here, are going to repel the electrons down here, pushing our structure in closer together. Now, these guys both have protons. So there are protons and electrons. So these electrons are attracted to the protons in the center of the atom. There's no protons on this lone pair, so they are essentially more negative. So they push in, all right, at less than 120, we call that bent. Let's say I have 4 things around my central atom, AX4. So if I have 4 things around my central atom, what if they are 1, 2, 3, 4 bonding pairs? Okay, 1, 2, 3, 4 bonding pairs, meaning 4 bonds. This is called tetrahedral. It has an angle of 109.5, and we would draw it to look something like this. So this does have an angle, is tetrahedral, and our angle is 109.5, and you can see this is a 3D structure. So I have structures coming up. This one's going out away from me. All right, let me see if I can't get it in. You can see it a little better. All right, one's coming out towards the right, one's coming towards me, and also towards the left. All right, so these are 3D structures. What if I remove a bonding pair? I still have 4 things around my central atom. I have 3 bonds, and I have a lone pair. All right, so now I have 3 bonds and 1 lone pair. In this case, we call this trigonal pyramidal. And it's going to have an angle of less than 109.5. And it would draw something like this. So I have 3 bonding pairs, 1 lone pair. This lone pair is pushing all of these bonds in closer together to each other, all right, because there are only electrons. What if I remove another bonding pair? All right. So in this case, let me see if I can't get it to where you can see it. There we go. So now I have 2 lone pairs and 2 bonds, which we call bonding pairs. 2 lone pairs and 2 bonding pairs. This shape is also bent. Again, is going to be less than 109.5. And it's going to be even less than the trigonal pyramidal. All right, and it's going to look something like this. So what we have is we have 2 lone pairs, very negative. So because we have all of those negatively charged electrons, it pushes our 2 remaining pairs in much closer together. Now, a bonding pair, it is important to note, a bonding pair can be a single bond, a double bond, or a triple bond. They are still one bond, and here's my analogy. A female, if she is pregnant with one child. How many pregnancies is she pregnant? One. She has one baby. If she is pregnant with twins, she is still pregnant one time. She happens to have 2 children. She's only pregnant with those 2 children once. She has 1 pregnancy, 2 children. If she is pregnant with 3 children, triplets, she is still pregnant one time, 3 children all at the same time. 1 pregnancy. So the pregnancy is the bond, okay? A single bond, a double bond, a triple bond, they are all still considered only one bonding pair. So don't let that trick you up.